Hello, linear algebra student. This video is for chapter 3.3, part 2. Continue with talking about how to find area of a parallelogram if you are given vertices. And in this question, we have 4 points, and we want to find the area. And what happened is the theorem said if we move the vertices so that the vertex the area basically is the same as moving one vertex to 0 0, then we can actually use the determinant of the two vectors at the two sides from 0 0, and then the determinant will determine the area. Okay, so let's just do an example. And if it is a 3 by 3 matrix, it will be a parallelepiped, kind of like a similar to a rectangle, but slanted kind of rectangle. So it's called parallelepiped, like that. And then the volume is actually the determinant of A, constructed by the 3 vertices other than the one from 0 0. This is an example where it is a 2 by 2 matrix. Can be the area of a parallelogram can be found by a 2 by 2 matrix. So these 4 points are not on the vertex. So we want to try to move them to so that one point is on. So we'll just use this one. You divide 2 plus 2, so this become obviously on 0 0, right? But because we move this, so the whole thing has to move. It's kind of like transformation. You move the whole thing plus 2, every single one of them plus 2. So this become a vertex at 0 0 corresponds to the point O here. And then the second one would be 2, you do plus 2, 5. And this would be plus 2 will be 6, and then 1. And then the last one will be 8 and then 6. And you can tell that x6 is a vector that is formed by adding the first vector u and the second vectors. 2 plus 6 is 8. 5 plus 1 is 6. So they always match. Otherwise, it's not a parallelogram. If this is not x6 but somewhere here, then it will be just a quadrilateral but not a parallelogram. So one of them is in 0 0, and this is u plus v. If we name this as u and v, right? So then the area would equal to actually having this 2 matrix in a column, 2, 5, 6, 1, and then do the determinant. So that would be 2 minus, the absolute value of this. 2 minus 30, the absolute value of 2 minus 30. I should say the absolute value of the determinant of this. So that would be absolute value of negative 28. Area is always positive, so it's 28, whatever units that they have. If we have a 3 by 3 points on the 3D space, so here, this is one where we have one vertex already on the origin, and then this is the 3 points. They didn't give the 4 point. You can figure out that it is a parallelepiped. If you want to, you can add them together. So how do I do? So the area would be all these 3, 1, 3 is 0, negative 2 is 0, 2, 1, negative 1, negative 1, 3, negative 1 is the absolute value of this determinant. So use the calculator. 1, oh, I didn't enter it. 1, 3, 0, negative 2, 0, 2, negative 2, 0, 2. The last one is negative 1, 3, negative 1, negative 1, 3, negative 1. Determinant of it is negative 18. So absolute of negative 18, that means the volume is 18. Oh, not area. Gosh, it's volume. So you can see that determinant is very useful to find these. And if you're interested looking at linear transformation, another example of linear transformation, you can look at the book. They have a description of linear transformation using the parallelogram. Another thing that is interested in knowing is the Cramer's rule and the way to solve system equation is actually quite used in Laplace transform. So if you look at the textbook page 180, do I have it open? So if you look at the textbook 180, I didn't talk about it, but I think it's worth mentioning. Why are we solving our system equation this way? Because we have actually here. They say that important engineering for a number of important engineering problems, particularly in electrical engineering and control theory, when they can be analyzed by Laplace transform, this approach converts a linear differential equation into a system of linear equation with coefficients involving a parameter. So sometimes we have a system, but actually we have parameters. So it's worth looking at a system like this where it is actually not a system of the equation of constant, but parameters, and we would try to figure out what this parameter would be to have a unique solution. So it is related to Laplace transform. So you can read this example. I have a question on the worksheet for you to do this kind of question. So, but it's pretty straightforward. So to have a unique solution, the coefficient matrix must be invertible. So basically, you do the you find a determinant of A to make sure that it is not zero. Okay. So that's all for 3.3.